This is the end, beautiful friend.
In this lecture, we'll say more about properties of ideals, finishing up the discussion in section 7.4 of Dummett and Foote. So at the beginning, I just want to recall an assumption from last time. That is, throughout all of section 7.4 in Dummett and Foote, R is a ring with identity 1 not equal to 0. So this really is important here. There are some statements that we'll say, or there are some statements that are given in Dummett and Foote that are just not true if your ring doesn't have an identity. And this assumption isn't stated in the statement of every proposition. So you need to be aware that anything that's happening in section 7.4 has this assumption with it. Okay, so let's get started by talking a little bit about ideals in fields. Proposition 9 on page 253 says, let's say I is an ideal of R. I is equal to the entire ring R if and only if I contains a unit in R. Okay, so this is the first place where what is a unit? That's an element U such that there exists an element V in R, where U times V equals V times U equals 1. So this is not a statement that even makes sense unless you assume that R is a ring with identity. Okay, so if an ideal contains a unit, then it is the whole ring. If an ideal does not contain a unit, then it's not the whole ring, right? Because it's missing all the units. So in particular, it's missing 1. Okay. Next statement, let's assume that R is commutative. R is a field if and only if its only ideals are the trivial ideal and the entire ring R. So this statement goes two ways. The only ideals in a field are the 0 ideal and the whole ring. And for anything that's not a field, you have at least one other ideal. Okay, so R being commutative is important. Remember, what is a field? A field is a ring with identity so that every non-zero element has an inverse and multiplication is commutative. So you can only talk about something being a field if you know it's commutative. The non-commutative analog of being a field is being a skew field or a division ring. Okay, so let's prove these things. There's two directions to each statement. One direction is easier than the other. So if you have an ideal that's the whole ring and your ring has a 1, then that ideal has 1. So I contains a unit. So there's nothing to do. So the other direction is more interesting. If I contains a unit, we want to show that it's the whole ring. So if U and I is a unit, by the definition of a unit, that means there exists a V in R such that V times U equals 1. And since I is an ideal, in particular, it's a left ideal. So if you have U in the ideal and V in the ring, that means that V times U is in the ideal. But V times U is 1. So 1 is in the ideal. Let me make this more clearly into an I. So 1 is in the ideal. And since I is an ideal, once you contain 1, you contain everything. Because 1 is in the ideal, R is an arbitrary element of the ring. R times 1 is equal to R is in I for all R in R. So I contains the whole ring, so it is the ring. Okay, let's do the second statement. Let's first assume R is a field. In a field, every non-zero ideal of R contains a unit. Why is that? Because every non-zero ideal of R contains a non-zero element of R. And every non-zero element of R is a unit. So once you know that every non-zero ideal contains a unit, then applying to part 1 says that every one of these non-zero ideals is the whole ring R. So the only ideals in the field are 0 and R. All right, so the other direction, let's suppose that the only ideals of R are the trivial ideal and the whole ring R. And we want to show that R is a field. So we want to show that every non-zero element of R is a unit. Okay, so let's pick some element U in R. So let's say I want to put in another assumption here. Let's say u is not equal to 0. All right, so what does that tell us? Let's take an ideal that we can build out of u. Let's take the principal ideal generated by u, and that's the whole ring R, right? Because it's not the 0 ideal, and the only ideals are 0 and R. So what does that mean? That means that in particular, the ideal generated by u contains 1. And what does that mean? Well, because we have this principal ideal in a commutative ring, so here it's important that R is commutative, that means that there exists a V in the ring such that V times U equals 1. Why is that? In a commutative ring, a principal ideal generated by U is all the things of the form something in the ring times U. Okay, so what does this mean? There exists a V in R so that V times U equals 1. Well, this is commutative, so also U times V equals 1. And U is a unit in R. So what have we seen? We've seen that any non-zero element in the ring is a unit. So R is a field. All right. One immediate consequence of this statement is the following corollary. If R is a field and you have any non-zero ring homomorphism, phi, from R to S, where S could be any ring at all, it's automatically injective. All right, why is this true? Well, the kernel of any ring homomorphism is an ideal of R. So if R is a field, we know that there are two possibilities. It's either 0 or it's R. And it's not all of R, because what does it mean for the kernel of a homomorphism to be the whole ring? It means you're sending everything to 0. So it is it's not a non-zero ring homomorphism, right? It actually is sending everything to 0. So we know the kernel is not R, so it has to be 0. And ring homomorphism is injective if and only if the kernel is 0. So that's the end of the proof here. So what are we seeing with these statements about ideals and fields is that the ideal structure in a field is trivial, that there's nothing interesting to say about the set of ideals contained in a field. You have as few ideals as you could possibly have, just the trivial one and the whole ring. So there are still interesting things to say, even though all of these homomorphisms going out of fields are injective. For example, you could ask, here's a field, what are all of the automorphisms of the field? A ring homomorphism from the field to itself. And that's something that'll come up much more when we talk about fields in detail in 206 B and C. And one last thing. So here we have this assumption that R is commutative. What if you ask for the non-commutative analog of proposition 9 here? What does it mean if you have a ring that has an identity but is not necessarily commutative and all of its two-sided ideals are the trivial ideal or the entire ring R? And Dummett and Foote have a short discussion about this. And the short answer, I'll let you think about this more, is that in the non-commutative case, things are not nearly as straightforward. So I'll pause and erase, and then I'll give one of the key definitions for this lecture, the definition of a maximal ideal, and then we'll talk about examples in Z, the ring that we know best. One of the main goals for the rest of this lecture is to study two special kinds of ideals, and we'll define the first one here. An ideal M in an arbitrary ring S, so I'm using S instead of R because we are giving this definition just for a general ring S. It doesn't necessarily have to have an identity like much of the other stuff that is in section 7.4 of Dummett and Foote. So an ideal M in an arbitrary ring S, not necessarily having an identity, is a maximal ideal if M does not equal the whole ring S, and the only ideals containing M are M, which contains itself, and the whole ring S, which contains every ideal. All right, so to get a feeling for what this condition on ideals is getting at, let's look at the simplest example we can, R equals Z. We know that the only ideals in Z are the trivial ideal, and then NZ, where N is a positive integer. So let's try to figure out which ideals are maximal. So we need to know when is one ideal contained in another. Well, this is something we've already seen. All these ideals are principal, and we saw that mz is contained in nz if and only if m is contained in nz, right? Once you have m in nz, then because it's an ideal, you get all of the multiples of m. So you get all of mz contained within nz, and the other direction is true as well. So when is it true that m is in nz? Well, that means that you take all these multiples of n, and at some point you hit m. So that means n divides m. So mz is contained in nz if and only if n divides m. So bigger number, smaller ideal. Right? M is the bigger number if n divides it, bigger number, smaller ideal. So what does that mean? Maximal ideals are going to be ones mz where the only things containing it are mz itself, like take m equal n, or take n equals 1, get the whole ring z. So the maximal ideals of z are exactly mz, where the only divisors of m are 1 and m. But we already have a name for a number, a positive integer, whose only divisors are 1 in itself. That's what it means to be prime. So the maximal ideals of z are exactly pz, where p is a prime. This is an example where we can classify all of the maximal ideals pretty easily because we know what all of the ideals look like. For more complicated rings, it's not so easy to say what all of the maximal ideals look like.